Now, in the earlier class, we had seen that how to use Jacobians to identify independent Maxwell's relations for our thermodynamic systems. So, in this current class, what we are going to do is we are going to look at how we can manipulate partial derivatives in thermodynamic systems, and you have seen quite a lot of them. Starting from the first law, we have derived equations. So, for the generalized equations of state as minus Fi over T, where Xi is a generalized coordinate and the corresponding Fi is the conjugate force. For a hydrostatic system, for example, P is conjugate, the pressure is conjugate to the volume, the particle number is conjugate to the chemical potential. So normally for a hydrostatic system, this is the one pressure volume which plays a very significant role, and therefore one defines specific heats as Cp and Cv. So essentially this is a specific heat that is defined for keeping pressure constant, and this is the specific heat that is defined by keeping volume constant. For any arbitrary thermodynamic system, one can have Cfi and correspondingly Cxi. For a hydrostatic system, this is very easily experimentally accessible, and therefore one defines this. So now, first let's see, I want to find out what this ratio is, number one. On top of this equation of state that we had defined for a thermodynamic system, it also follows that there are various response functions that we had seen. One of them are, of course, specific heat. For a hydrostatic system, you also have the compressibility kappa T, which is minus 1 by V del P, temperature constant. One can also define same compressibility, in which case entropy is held constant. This quantity is called adiabatic compressibility, and this is called isothermal compressibility. Now you should know that it is this compressibility that appears in speed of sound in a fluid. Other than that, of course, you have alpha T, which is del V del T 1 by V. This is the expansion coefficient, the volume expansion coefficient that you defined. If you change your thermodynamic system, these definitions will change. For example, for any arbitrary thermodynamic system, if you have Fi as the generalized force and the conjugate generalized coordinate is this, well, one should say the other way around, the generalized coordinate is Xi and the corresponding generalized force is Fi, then one can of course ask del Xi, del Fi, and this experiment one can do either keeping the temperature fixed for an isothermal process, or one can define it as del Xi, del Fi by keeping the entropy fixed, right? For if you look for other example, for example, for a magnetic system, you have magnetization as the coordinate, thermodynamic coordinate, and magnetic field as the force, in which case you essentially have del M del B, temperature constant, and del M del B. This quantity is called the magnetic susceptibility. This is the adiabatic susceptibility, this is the isothermal susceptibility. Typically in experiments, it's always this quantity, the isothermal compressible susceptibility, which essentially plays a role, right? So for a hydrostatic system, these are essentially susceptibilities. How does your generalized coordinate behave if you change your generalized force, right? So if you want to write down for any isothermal process, any isothermal process for such a system, or for any arbitrary, let's say for any arbitrary system, if you want to write down dxi, how your generalized coordinate has changed, then essentially you write it down as del fi temperature fixed dfi. So this is how your thermodynamic coordinate should change if you change your thermodynamic forces. So you see, partial derivatives are all around in thermodynamics, and one needs to know how to manipulate such derivatives. Jacobians are of course a very good way of doing that. On top of the Jacobians, so number one is you can use the Jacobians. The second quantity that you frequently use is the cyclic relation. Do not forget that. What does the cyclic relation say? Del x del y z constant, del y del z x constant, and then you have del z del x y constant must be -1. So one frequently replaces x, y, z according to the quant relations one wants to find out. So now coming back to this, I want to find out the ratio of Cp over Cv. Cp is defined as T del S del T, pressure constant, and Cv is defined as T del S del T, volume constant. If you want to know how do they come, well, Cp is d cut q over dt, pressure constant, and Cv is d cut q over dt, volume constant, and d cut q from second law of thermodynamics is Tds, and therefore you have del S del T, pressure constant, and this one you have T del S del T, volume constant. So clearly the ratio of Cp over Cv is del S del T, pressure constant, divided by del S del T, volume constant. There are several ways of finding it out. I want to illustrate the cyclic use of the cyclic relations. Here I have S, derivative of S entropy with respect to temperature, pressure being held constant. So I want to use X as I want to replace in the periodic, in the cyclic relation, I want to replace X by S, Y by T, and Z by pressure. That means this gives me, let me change the color here, del S del T, pressure constant, then you have del T del P, entropy constant, and then you have del P del S, temperature constant, is equal to -1. So therefore you get del S del T, pressure constant, is equal to del P del S, temperature constant, divided by let's see, well, we want to write that properly here. So del S del P, temperature constant, times del P del T, entropy constant, with a minus sign. Similarly, for this I want to again use the cyclic relation volume. So del T del V, entropy constant, and then you have del V del T, sorry, I have already used that, del V. So T has come once, V has come, T has come twice, V has come twice, this has to be del V del S, temperature constant, is equal to -1, which means del S del T, volume constant, is del V del T, entropy constant, del S del V, temperature constant, with a minus sign. Therefore this ratio is now del S del P, temperature constant, del P del T, entropy constant, divided by del V del T, entropy constant, del S del V, temperature constant. Now the minus sign has cancelled out. So let us collect terms with the fixed quantities. Del S del P, temperature constant, and then I have del V del S, temperature constant. These two terms can be grouped together. This can be grouped together because they have the temperature fixed in both the cases, and similarly these two can be grouped together because they have the entropy fixed. So therefore I have del P del T entropy constant times del T del V entropy constant. This I know. Del S del P del V del S is del V del P temperature constant, and this is, if you are careful to see, entropy is held constant. This is del P del V entropy constant. Remember, what we are using now is del X del Y Z constant. This is the reciprocal relation. Del Y del X Z constant is equal to 1. Okay. Right. Therefore, Cp and Cv is equal to, so you can also say that del X del Y Z constant, del Y del U Z constant is actually del X del U Z constant. This is also what we are using over here. Now it follows, therefore, that the first term is del V del P temperature constant divided by, I have del P del V entropy constant. Let's rearrange and bring in a minus 1 by V, and you'll see that this is kappa T over kappa S. So the ratio of the two specific heats, Cp over Cv, irrespective of the system, is equal to kappa T over kappa S. Right? So this is how you manipulate partial derivatives. What about this quantity, Cp minus Cv? The celebrated relation that you found out as R. I want to derive the general expression for this. So for this, let's start off with Cv over T. Now Cv over T is del S del T volume constant, which I write as del S comma V del T comma V. Right? There is no problem in writing that. I will rearrange this Jacobian to introduce del T del P del T comma P del T comma V. Right? It's the first one. The second one I know what it is. So first one is del S del T pressure constant. See, I'm a little bit careful in introducing the pressure because I want to relate Cp and Cv. What I have got on the left hand side is Cv by T. I want the right hand side to be Cp by T, which is del S del T pressure constant. Therefore, I have brought in T and P. That's how the original thought process was. So del S del T pressure constant. This is, if you want to evaluate this Jacobian, then this Jacobian has a very simple form, del S del T pressure constant, del S del P temperature constant, then I have del V del T pressure constant, del V del P temperature constant, the determinant of this. So then if I evaluate this determinant, I write down del S del P pressure constant, del V del P temperature constant minus del S del P temperature constant del V del T pressure constant, and this one I have del P del V temperature constant. So life is very simple now. What I have in the left hand side is del S del T pressure. If I open the bracket, this multiplies with this, and if you use this relation over here, then essentially I have del S del T pressure constant minus del S del P temperature constant del P del V temperature constant del V del T pressure constant, right? This is del S del V temperature constant del V del T pressure constant. So let's see, do I have anywhere del S del V which I can use? All I have to figure out is what is this derivative, right? So for this I have SV. I want to now see, here comes the utility of the Maxwell's relation. I want to figure out if there is a Maxwell relation that relates this derivative with something else. But this structure of this derivative, so if you just look at the structure, del S del V temperature constant, this immediately tells you that I have S dt, correct? Then I have V dP. So what is then, I have to figure out which one I can use. So if I just look at dF, which is U minus Ts, is d of U minus Ts is minus S dt. Recall your first law again, du is equal to Tds minus Pdv plus mu dn. So du minus Tds, if you bring it this side, it's minus Pdv plus mu dn. So now you see, if I want to write down the Maxwell's relation for this too, I have del S del V temperature held constant is equal to del P del T volume held constant. So this is how you go back and forth from the derivative. What you have in the structure of your partial derivative, you have to figure out whether there exists a Maxwell relation. So I can clearly see my Maxwell relation tells me that del S del V temperature constant is del P del T. So I will do, I'll simply replace this by del P del T volume constant del V del T pressure constant, right? What is del P del T volume constant? This is still a quantity which I have to figure out. But then let's apply the cyclic rule. Del P del T volume constant del T del V pressure constant del V del P temperature constant is minus 1. So del P del T volume constant is del V del T pressure constant divided by del V del P temperature constant with a minus sign in front. So then I use this relation over here. So this means this is del S del T pressure constant minus del V del T pressure constant divided by del V del P temperature constant times del V del T pressure constant. This becomes a plus. It is here that I have to figure out something. So what I do here is I multiply this by volume, divide this by volume, right? So now if I have to multiply it by V square here. Now you see kappa T is minus 1 by V del V del P, temperature constant, and alpha P, what did I define the response function here? Let's see. Yeah, sorry, this has to be alpha P because you're taking a derivative with respect to temperature. So this has to be alpha P. Please be careful, because you're taking a derivative with respect to temperature, so temperature cannot be held constant there. So del V del T, pressure constant, right? So this is del S del T, pressure constant, minus V square alpha P square divided by V kappa T, right? Which is equal to del S del T, pressure constant, minus V alpha P square over kappa T. The left hand side was Cv by T. If you look at this structure of this, the first term is actually Cp by T. So Cv by T is minus V alpha P square over kappa T. It follows therefore Cp minus Cv is T V alpha P square over kappa T. This is the general relation for any hydrostatic system. Whether it is an ideal gas or a non-ideal gas, you should always have this relation. So there are two essential relations. One is Cp over Cv, which we saw was kappa T over kappa S. The other one is Cp minus Cv. So if you know these response functions, you also know the specific heats. Correct?